The FFLD stands for Fused Fiber Layer Deposition of Lunar regolith.
It is important to use the material that is available on the moon and have a very efficient way of manufacturing parts in situ.
It takes a lot of money and effort to take kilograms or any construction material or any material to the lunar surface. If we have a possibility to create materials directly from the resources that are available on the surface, that will address that issue.
It was very fascinating to see that one material which is present on the moon in abundance, lunar regolith, can become so many different things and so many different materials.
The Fused Fiber Layer Deposition project explores how lunar regolith can be transformed into useful objects through additive manufacturing and whether fiber reinforcement can improve the mechanical performance of printed components.
We wanted to study if adding fiber strands would improve the tensile strength of the parts and open up new application for the building blocks, which will be used for building habitats, roads, landing pads on the moon.
The project brought together 3 partners, each contributing a distinct field of expertise. The University of Aalen led the research, focusing on engineering science, material behavior, and the development of the additive manufacturing process. Liquifer, a space architecture company, explored architectural applications and future lunar scenarios. RWTH Aachen contributed expertise in textile processing.
This interdisciplinarity helped us to brainstorm and to look at all different perspectives and to ensure that whatever process we develop makes sense in a real lunar application.
The project explored whether continuous fibers could be embedded into the molten regolith during printing, creating a composite material directly on the moon. At the heart of the project is a customized 3D printer designed to extrude molten regolith. The material is melted and deposited layer by layer inside an annealing chamber, allowing internal stresses to be released as the part cools. Earlier attempts to 3D print lunar regolith using microwave laser or solar energy demonstrated feasibility, but also revealed persistent challenges, including cracking and high internal stresses.
During the FFLD project, we have demonstrated that these cracks can be avoided by annealing processes, which is a thermal post-processing of the printed samples and improves the mechanical properties and quality of the final products.
The printing campaigns tested different geometries, fiber types, and process parameters while analyzing mechanical performance, microstructure, and energy consumption. The experiments revealed a fundamental challenge. Annealing produces strong, glassy regolith structures, but the prolonged exposure to high temperatures causes embedded fibers to degrade. Without annealing, fibers survive, but the regolith remains brittle. The project used this insight to redefine the research direction. The focus shifted from embedding fibers directly into molten regolith to understanding what the printing system could reliably produce and how alternative fiber-based strategies could expand its potential. Fibers were explored as casting templates, woven stabilization mats, surface imprinting tools, and hybrid reinforcement systems. The resulting applications are broad.
If you think what we have here on Earth, that it's glass or ceramics, this is basically what we can do with the material that we're developing. So it can be like tiles for lunar habitats, either for exterior or for interior, construction composites, road tiling for rovers to drive on. But it can also be smaller scale, so glassware or kitchenware or even laboratory equipment.
Looking ahead, the next steps involve scaling up production, testing under lunar conditions, and integrating these processes with autonomous systems.
There are additional questions that need to be solved. For example, how the entire process that is currently done on Earth is behaving under partial gravity and also under a vacuum condition that are available on the moon.
From architecture perspective, the next step would be scaling up the process to be able to produce bigger samples, but also more samples in a shorter period of time, but also controlling the form of what we're producing.
By revealing both the possibilities and limitations of fiber regolith manufacturing, the project helps define realistic pathways toward lunar construction, contributing one step in a longer roadmap for sustainable in-situ infrastructure.
It can be a whole diverse, different materials and world of regolith products on the moon.